As I said, I'll avoid using the vectors, but that's implied. That's because I'll run out of symbols which can be legible. And there could be a forcing, but so this was the equation. This, I hope this you'll recall. Then so these are the properties I will use. As I said at the end of the previous class, I mean, there will be some properties I'll use which I may not prove for you guys because that may not be of great interest, and you can, if you're interested in doing this rigorously, you can always go back or ask me how to prove it, or you can prove it yourselves, I'm sure. Okay. There'll be another set of properties, I'm hoping. I'll be able to write down there in due course. And so I'm just going through what we did yesterday, just setting down the equations. As long as you all have a sort of feeling for it, that's fine for me. Some of you in the audience will have more than a feeling for it in the sense that you all are experts in these things. So this allows me to think about the coarse-grained velocity field, which I said was like filtering. So you sort of pick up only scales up to a point. So maybe I should also write down we use these sort of properties to define essentially I'm just not writing R by L every time. So physically, what does this mean? Physically, as we said, the velocity field is defined point-wise. So this is just recalling the construction. So you saw all these formulae, etc., in the previous class. So I have this kernel, which I've defined, which we defined in the previous class. Just to refresh your mind, the kernel is smooth. It has the following properties. That's the Navier-Stokes. And the kernel has these additional properties. So this allowed us, if you remember, to define this sort of coarse-grained velocity field at a scale L. So in some sense, this is, I can never remember it's high pass, low pass. I mean, in the frequency space, it is allowing only the lower frequencies to go through up to scale 1 over L. So what this does, I mean, just intuitively, physically, if this is my velocity field, I'm sitting, let's say, in this grid, then I've put this kernel on top of the field. You can think if you want this to be a Gaussian, it really doesn't matter, which is sort of going away far enough. And so I'm sort of integrating the velocity on top of this kernel to get an effective sort of coarse-grained velocity field. And then I think we sort of eventually derived in the last class what were, this was the notation that we had used, which was just the complementary high pass velocity filter for this guy will just be equal to that really wouldn't matter. Again, remember, I'm not writing the vectors everywhere. The velocity field is vector. If what we'll do eventually when we calculate the norms, the vectorial nature will disappear. And this was okay. You remember how we got there, right? We took this, this is equal to just v of x minus this because of the property of the kernel. I can take the v of x inside, take the negative, that gives me the velocity difference, and I write it down.
Is this same as convolution?
Well, I mean, I haven't done any transformation, but you're convoluting with a kernel function. Yes, so you don't have to worry about the semantics so much. All right. And remember, we had also looked at some empirical results, which we derived from soft theory. One of them had to do with that, the fact that the square of that delta V goes as R to the power 2/3. That was something we had derived from soft theory. All right. So let's see how far we can go ahead with these manipulations. So we had also sort of use this on the Navier-Stokes. This is, I'm still sort of recalling earlier stuff. And we were, if. So there you have the integral R GR is equal to and R squared TFR is what? Property of this. Yeah. Take the mean moment of a smooth function, which I'm just writing down the basic properties which I'll use since we have to finish certain things in 2 hours, so we'll just use these properties. As I said, at the break at 3 o'clock or after the class, if those properties sound opaque to you, we will come back and derive them. All right. The other thing that we sort of, and this is where we ended in the last class, I think, was the fact that we were able to write down using this a large scale motion, which was essentially looking exactly like the Navier-Stokes. I'll keep some space here. With an additional term, which was the effect of actually this close grading, and that sort of results in a certain forcing on the field, which we were able to interpret as the effect of the large scales driving the flow. So that was a bit like, for those of you who have a sort of engineering background, I mean, many of you do here, etc. So that form will remind you of what's known as Reynolds stresses and things of that sort. So this is where we essentially were. All right. So at this stage, the question is, what happens when L is large or viscosity is small? Right. I mean, viscosity being small is the problem that one wants to understand, right? Viscosity being large is an important problem, no doubt, but at least, the problem that we sort of building ourselves up to is the case when viscosity is small. So let's try and understand from this equation. So before that, let me so here's another set of properties. Again, you probably know some of these. So if I have some function f, I'm going to use these notations, but I'm going to define them here for you. And I'll give you some physical meaning of some of these notations. For some of them, I do not have a physical sort of picture to provide, not because y'all will not understand, but that's because I do not know how to provide it. All right. So the ones that I can, I will. The rest, these are manipulations that will be useful. So every time, so f is some function, not necessarily the force. So maybe I should write, G is the kernel, right? Okay. Okay, maybe I'm just using a function f, which is some function f. So these two parallel bars on either side is the standard notation to define what is known as a norm. This p, you will see where this comes in. Maybe I'll just give the definition. Arun, is this going way beyond where you can?
It's okay.
It's okay. It's still okay? Okay, fine. So I'm going to define things in terms of this F norm. So stare at that. When you stare at that, you realize that I'm trying to be more sophisticated than I should. And you can go back and tell me, all you've done is you've integrated things, taken the function, taken its modulus so that you don't have to worry about how to raise it to some power p, done the integral, then did a 1 over p because you wanted to, keep dimensions sort of consistent so you can compare things as it were. That's precisely what I've done. So for example, if I choose p equal to 2 in this, and let me make the game easier for you, and let's say f is some velocity. So let's say this. So I've taken p equal to 2. What will that signify? Velocity, I've taken square, I've integrated an average everywhere, then taken a square root. That's the RMS velocity, for example, right? So you see, I'm trying to be fancy, but you can understand what I mean, right? Then if I take this, what will that be? It's the URMS, but now I take the square of that, so that will be something like an energy. So sahi salamat. Okay, so that's how one should interpret. The good thing is, there are several good textbooks on functional analysis. I'll use some results, a couple of those results, which you have to sort of, where your overriding sentiment is that hopefully I remembered those results correctly, wrote it down in my notes correctly, and then I'm going to hopefully write it down correctly. If not, I'll find contradictions in what I do. So I think we are on good ground. So that's what a norm is. So norms have some, these properties. For example, the way I've defined it, I mean, there are certain subtleties, but let's not worry about, I mean, these will make sense to you guys. Is, for example, this will be greater than 0, right? Because I've taken some of it. Of course, it depends, but for the function that we'll use, we've used a mod. Of course, this is 0 when the function itself is 0. Then you can, you can immediately guess which are the ones I'm going to use, sort of. This, if alpha is some scalar number, then it will be nothing but a multiplication of this. It could be a complex thing, then I want to put the modulus on top of that. And then it won't surprise you, for example. Have you seen, for example, something looking like the last one anywhere? Sorry? So you all have seen things which sort of smell and look like what I'm doing, right? Okay, great. So you can use these ideas and construct these norms. So you can actually go back to the Navier-Stokes, and then these sort of results go back to various sort of mathematical papers, and maybe I should give some references. So those sort of things, you can pick your favorite book on functional analysis and try to apply. Then there is a book by Gibbon and Dering, which you can sort of use to understand analysis. And then there are very nice papers, which is where we will end up today with some luck, which has to do with work going back to Peter Constantine, Greg Eink, etc. in the 90s. But okay. So what you can show using these norms is, for example, So how do I interpret this? I mean, these are the results that you'll get from some more labor, but how I'm interpreting this is just purely, you can see that dimensionally, this will pull down factors of L squared that I have, gradient, because I'm cosining it at that length scale. And then you can show that this is going to 0 if Vp remains finite. All right. Now, we will see that there's an apparent contradiction. Sorry? Yeah, I'll come to the NEP part of it. Yes. For the moment, the way I've written it, it's true for NEP. But we'll see that one of those limits will become a problematic for NEP, and that will give you essentially what you probably have in mind, the P equal to 3 case. So what this essentially tells you is that if my velocity, forget the maths, just the physical intuition makes perfect sense in the sense that I'm actually taking this function, integrating it in the way that I've told you. The viscosity comes out of this because that's just a constant. Remember, alpha F is, you can take alpha out. And then you can sort of argue that if this chap goes to 0, in some way, then this whole, and this has a finite value, then this whole function must be 0. We discussed in the previous class that there are cases, especially in the Navier-Stokes or Euler world, where the dissipation rate itself doesn't go to 0 when viscosity goes to 0. So we start with this result and we try to understand something along the lines of what Anupam was suggesting, something along the lines of where this sort of seemingly obvious statement kind of breaks down. All right. Yeah.
Is norm here analogous to finding length of some n-dimensional vector?
Well, not just the length in a Euclidean sense, because I'm taking the power of it. But for example, if I take P to be 1, and then I'm taking the average of the function, so it's not exactly the same, but if you can think about a curve, right? And this f of x is some sort of a curve, then you can think about it in terms of length. Okay, great. Okay. So what we need for our dissipation game is right. So if you calculate this in this way, then we rederive what we did in a previous class, which had to do with energy balance from the equation. Remember, we took the Navier-Stokes, we multiplied both sides by V, etc. Right? Then we took the ddt, V dot ddt of V is ddt of half V squared. The nonlinear term integrates out to be 0 once you've taken this product, and all you're left with the nonlinear term. So in writing in this language, if you remember the previous thing, then you just end up with this expression that we already had. That the rate of change of energy will be either 0 or it will be a decreasing function. Right? That's because the grad V squared, this norm will be strictly positive. And so the minus sign that we get. So this is something that we'd already sort of seen in the previous class, and that's what we have there. All right, very good. So let's come back to the equation, and then let's start doing some manipulation. I'll worry about this term a little. So what is this term? All right. So one way to think about this term is, again, you can play the same game that we did with Navier-Stokes, which was take the multiply V and see what the flux is. But let's try to do it from a slightly different point of view. So all of you remember roughly how we define the flux, but I'm now going to define it in this coarse-grained field, right? The flux was defined in the first class when we did the phenomenology, and we sort of talked about some amount of energy epsilon going in, some amount well, the same amount in a statistical sense leaving. And we showed that there was this whole intermediate range of scales, which scale with Reynolds number, how big that range is, where there's a constant flux. So we can try to use this sort of idea to try and estimate what the flux will be. So essentially what you will have is the following. So let me just write down a couple of properties for deriving this. Is the following. So you have to work. That's the flux of acoustic signal, which is going back and forth. The results, I have the references. The results I'm going to quote are from that's where you should look up. So what I will write down is the first set of results that we have here, and then we will, because this result is slightly trickier to analyze. So what we have here is the flux of energy. Those are the proofs that we had, is some constant at the scale in which you're looking at things. So the flux is bounded by delta V cube over L, and that really comes from the fact, and this is a simple game. We had the definition in the last class of what tau L is. So just plug in the quantities for tau L, and you will get an estimate that the tau L will be ordered delta V squared. So the flux is how much is this delta V squared getting transported in time. That's essentially the flux, and that buys you another factor of delta V over L, and that gives you delta V cube over L. This was exactly what we already had in the first class, but what people were able to do is, in a more rigorous mathematical way, was to say that the flux is bounded. The equality is what we had convinced ourselves previously, but now what we are saying is that it could be less than equal to delta V cube over L. So this sort of allows you to define essentially the total flux. And the total flux would just be the integral . So this is pointwise. So now I'm going to integrate it over all space and compute what the total flux is. Or you can even think about the mean flux, which can be useful, which will be nothing but so from this and the equalities and the properties that we have, what we can immediately write down, as I said, after we discuss things in the previous class, that we will go through the list of results and then try to connect it to the physical picture. What you can write down is just plug in P equal to 1 here and you get the same result, right? Because you take pi, take 1, that's like the average quantity, and you get the same result. So the question is, what happens if you take any of these, any other higher order norms? So for that, let me write down What's again, I won't prove what I know. So maybe a couple you may have seen elsewhere. So if you have two functions f of g and you take the first norm, then this function for we are slowly getting to the point that Anupam was making about what is the constraint that P has to satisfy. There's an equally powerful, and I think that is the one that we will mainly use, is there are too many bars that I'm drawing. If I take the norm of n functions, f1, f2, f3, etc., and take the rth norm of this, then this strip will satisfy all right. So if you take a sequence of n functions, you multiply all of them and take the rth norm. So you can, there's a quick check you can immediately do. Take all the functions to be like the velocity or something, take their products, plug it in there, take the rth norm, so replace p by r just for convenience. Then that must be smaller than if you take all of these individual functions, take suitable p1, p2, p3, etc. norm, such that the sum of 1 over pi, p1, p2, p3, p4, etc. is equal to 1 over r. Trivial check, do it for p equal to 1. That's where the equality will be satisfied. Now you take two functions, for example, and then if you want to play the game, you'd get this. Again, this is just one side. Again, this is kind of standard sort of result in this analysis. So these go by the name of Hilder inequality. So you're from maths, if I remember well, so you know everything about this. You can catch him also. Yeah, someone asked you. Yeah.
So we have this are inequality plus undefined inequalities, right?
Yeah.
So what will be our V for here if we are defining F as that?
What? Sorry, come again.
Is an inequality that you wrote,
Mm-hmm.
What will it be for that? Like, because F is defined as like that, right? 1 by V, and then you are integrating.
No, F I haven't defined, right? F could be any function.
Yeah, that's what I'm saying.
Huh?
So we have variable V there, right?
So you,
what will be that V?
F, you can take F to be V.
I think that's the volume.
Oh, sorry, you mean this V? Oh, I'm sorry. This is, sorry. This is my handwriting, sorry. Give me another year. Sorry, Anupam. Capital omega. I'll use omega for phase space. Okay, let's use capital omega for the moment. Sorry, this is volume. Sorry. Okay. That's it. Sorry. That's it. Okay. Yeah, that's why I was saying take P equal to you get URMS, etc. because that's sort of volume average. Sorry. Very good. Or not so good. So, with those inequalities, the most sort of key result now will follow trivially, and probably you know some of you may have already seen matlab, you know, once you saw these inequalities, you've already imagined where we are heading. So remember this key sort of result that we discussed maybe 2 classes ago about the Navier-Stokes. So now I'm going to just play this game. Once you know such inequalities, things become easier. This, okay, this is R. Okay, just to avoid further confusion. Huh? Maybe that starts to look like. All right. Sorry, huh? My handwriting is terrible. But that ship has sailed. This comes from the definition of flux that we had the previous day. Remember, we had this tau L, and then there was the multiplication. So we can write del the pi L. So pi L can be coupled into these 2 functions. So the flux becomes an inequality in terms of P1, P2. So I can, in principle, if this is R, then this sort of satisfies. I hope it does. Yeah, 1 over 3R plus 2 over 3R gives me 1 over R. Very good. So now choose P to be 3R. Okay. So if you now, so do you remember the grad VL that we had the previous class? Let me write it. Can I erase the inequalities or should I keep them? Just write down the final result because that will, I mean, just write. Anyway, I've given the final result for the inequalities. Yeah.
Please read it out. What is that summation PI? 1 over PI?
Oh, this will be equal to 1 over R, where R is the norm that I've taken here.
And there's something in the circle as well, right?
Oh, that this is strictly true for R greater than equal to 1. Which actually tells you the critical point there. Okay. So again, just go back to things that we did in the last class, which was in softer language. It's just that, especially for our friend from maths who's sitting there, we decided that we will try to sort of at least write down the exact inequalities. So now you can now let's look at the terms there. So first is delta V. All right. So delta VL, you remember. Now I will have to take a gradient. Right, that was how we had defined delta V. I've taken a gradient, so that sticks inside, and I've got a gradient of V. So now if you take the triangle inequality, which I had written there, then what you're essentially able to show is that again, don't worry too much about the exact form of what we are writing because I'm not doing the derivation at all. If you want a naive way to think about it, remember how we wrote down V bar in the previous class from the coarse grain velocity. I've just stuck in the gradient function on that formula, and I've taken the Pth norm. I haven't done anything more adventurous. So now, if you assume, so if you assume the exponent that we had, sum 0, why this bound will become very clear. And you assume that this guy, the one here, goes as C. Remember in the phenomenological thing that we are doing in the previous class, the sigma p was found to be 1/3, right? So that's all I'm doing, except right now I'm not writing down explicitly what it is, and I will see if that 1/3 emerges as a special solution which satisfies all these inequalities. All right. So, what we will get is I want to write down that integral because I had the sigma p sitting there. This thing will just be something which is order, right? I have an L to the power sigma p sitting for the delta V norm. I'm just choosing sigma p to be a number, which I do not know. We had seen sigma p to be not sigma p, but for the first order structure function, that to be just 1/3 in the previous classes. I buy a factor of L outside. So this is, let's assume this to be of the order of L to the power sigma p minus 1. This integral, etc. Let's say it works it out to be some simple thing. So similarly, we are already running a bit late because at 4 o'clock there's a talk that I think, I don't know if you'll have got some email. Just check the email that Rama has arranged a talk for them at 4. Yeah, just check your email. She will send an email by Michael Jordan on this sort of. Okay. Yeah, she had sent it out in the morning to us. Yeah. Yeah. Sorry? Oh, sorry, guys. Sorry. That's not theta. This is an O, which means of the order of. Okay. So, like my age is of the order of 100. So I'll write O and then 100. Huh? Okay. Yeah. Sorry.
Could you explain this minus 1 is fine?
So yeah. So I've assumed that this norm, the pth norm here, delta V. Remember, we had sort of got delta V squared going as 2/3, right? L to the power 2/3. That's the empirical thing that we had seen. And we had also done Kolmogorov theory where we had seen that delta V to the power P goes as P by 3, right? So I'm just assuming that I do not know what this number is, what the exponent is. Why this is that I'm allowing for however rough this field is. 1 would mean that things are nicely differentiable. 0 would mean there's no differentiability. So that's all I'm assuming. So this is another way to actually come out with the same results that we sort of got, actually a little better, because now certain sort of constraints on these exponents, which the soft theory doesn't allow, will be allowed. So similarly, you can estimate this to be not theta, but order L to sigma P. And here we have to take P to be greater than 2 because I've taken P halves, right? So this follows that the flux that we were after now, this is quite an interesting result. Why? That's because we are eventually, you remember our Reynolds number was scale dependent, right? We had defined the Reynolds number as some UL over nu where L was the scale. Now, if I'm going to go for the asymptotics of infinitely large Reynolds number, I'm trying to push my viscosity to go to 0, which means I'm trying to push my smallest scale, which goes to 0. We had defined these scales in the first class, right? The Kolmogorov scale, which we constructed from viscosity and eta, etc. So when you do that, and when you see this, then you see an obvious problem. What you see is that as L goes to 0, the flux, which will eventually be the quantity which is converted to heat and then dissipate, that guy will go to 0. So what do you see? What you see is, let's say, the mean flux. That's easier thing. This goes to 0, L going to 0. For all cases, unless all I can say is the negative result, really. Right. So let me come back to the soft picture. This part is the following. As L goes to 0, if the exponent sitting on top, the exponent here, if that exponent is positive, so a number to the power a positive number, and that number goes to 0, the whole thing will go to 0, right? However, 0 to the power something negative will actually diverge. Now, that divergence can be controlled in ways because how quickly does L goes to 0 with viscosity, that's a different question. So that's why I said I'll only make the negative statement, not the one about finiteness, which is to say that for sigma p, which is less than equal to 1/3, for p greater than equal to 3, the flux must vanish. All right. What does it mean? You remember we had looked at these experimental graphs when we did the Kolmogorov intermittency theory. We had this plot, right? Where, what is zeta p? Zeta p was delta v to the power p. I've used L, right? Okay. L to the power zeta p. And we had seen that Kolmogorov theory gave me this straight line, which is p over 3. All right. We know that there is an exact result for this to be 1, right? And we had seen that the number here is, let's say, 0.71. 71. This is about 0.34. Let's say this is 0. And then this deviates. So if you think about it, then zeta p is nothing but p sigma p. All right. Because zeta p, sigma p comes from the fact that I've taken the pth norm, which when I had defined the norm, I had taken a 1 over p on top. So it's zeta p by p. Okay, you guys are with me, right? So I essentially end up seeing that the experimental results that I have certainly suggest that the sigma p is less than 1/3 for p greater than 3. All right. So where am I getting this finite dissipation from? So where we are getting this finite dissipation from is slightly more convoluted. And maybe we can, after the break, I'll just finish this thing. We'll look at a more trivial example in the burgers where we will rigorously prove this. But what you certainly see is that this picture of the scaling exponents that we measure, and this is sort of, in any turbulence colloquium, etc., people show this graph. This graph, the actual data, is completely consistent with the fact that you have anomalous dissipation, right? As you see, this is, again, unless, not when. So if this holds, then this limit doesn't hold. Now, whether that limit is a finite number, which is what, experiments seem to suggest, whether we can estimate that finite number. So that, for you young people, is a major sort of outstanding question. So you guys can go ahead and actually find out what that limit could be. It's something that is still, unclear. And this is what's known as anomalous dissipation. Why? I mean, why anomalous? That's because that's slightly technical. The reason is that you've taken an equation which had no dissipation to begin with, which might have dissipative solutions distributionally, but not as strong solutions. You've added a viscous term. So you've broken the symmetry there. But now, even when you take that coefficient to 0, you do not get back the previous problem. All right. So to that sense, it's anomalous dissipation. And this is the sort of key result that you see theoretically, how you actually understand why this graph is consistent with the other curve we had seen, which was epsilon versus 1 over nu, which doesn't go to 0, but goes to a flat constant. Yes, Siddhartha. Sorry, come. Just plug it in, sigma, and then here you will, when you put in the inequality of PQ, because this came in from the fact that the flux I was able to write down in terms of the stress tensor and grad V. All right, so I used the second Young's inequality to actually show that the only time that I can actually make this valid is when P greater than 3. For P less than 3, I do not have a way to. Sorry, where? Yeah? Second column, last line. Yeah. Did I start with P by 3, right? Yeah. Yeah. Okay. So then P by 2 will be, okay, fine. All right, so what we have for the moment is the following strong statement. So there is something, rather interesting about the way we approach this problem. So when we actually get this result, we didn't rely on anything phenomenological. We did not rely on the fact that we only relied on that, even not so much on the fact that there's scale separation, to the extent that we constructed this kernel which sets a scale in the problem. But we did not at all invoke the fact which you do to derive Kolmogorov, that there is this range of scales where only epsilon or the scale matters. But just by using inequalities which could be applied anywhere else, we are able to construct this delta V, just from the coarse-graining of the velocity field. What we don't, you can actually make the inequality to an equality and actually derive the Kolmogorov result from this, but we are able to derive everything in terms of the mathematical structure of this curve and the fact that these two are related just from this one I mean, this is the most powerful result that one obtains when one plays this game. And, this was developed by, I mean, so what I've given is hardly rigorous. Huh? What I've given you is a sketch of how you actually go about deriving these results in very soft way using known identities, but there are more rigorous ways to actually show this, which at least some of you, I encourage you all to go and, Jiten.
So this is tending to 0.
This is tending to 0 as L tends to 0 unless this condition holds. Normally we write this tends to 0 as long as something else holds. All I'm saying is I'm giving the negative statement.
This is the reality, sigma p less than 1/3.
Is what we see in experiments, and then we know this cannot happen. And this is also what we see in a different set of experiments. So the fact that you have, and this is what's called intermittency, etc., colloquially, the fact that you have this departure from Kolmogorov, and the fact that you have this, the fact that the epsilon has a non-vanishing limit as L goes to, as nu goes to 0, are completely consistent with the structure of the Navier-Stokes equation. And where did that structure play a role? That precise structure played a role when we were coarse-graining the field and got the divergence tau L term out of it. So what you can do, I mean, I sort of thought I'll teach that, but I'm not. So I'm skipping some parts of it. What you can do is actually study this divergence tau L term very carefully. From there, you can get everything related to, well, a lot of things related to the scale-dependent Reynolds number, at what scales viscosity starts, how viscosity starts to matter, etc. But I think Jitendra, you were asking. Is that clear now, Jitendra? But this is what to me is a very beautiful result. The fact that you can kind of simply prove at least the bounds which are satisfied by experimental data. Okay. I mean, the key, the unsolved question, of course, is can you have a theory for the way this curve is? And that is an open sort of question, which is, how do you systematically, from the equation, show this curve? That's something that we cannot do. Distributions over? That is something similar to what was there yesterday in Ritik's talk, right? So what Ritik was looking at was trying to understand exactly this sort of question in the sense, yeah, except this quantity, okay. Anupam, let me discuss this at the tea break in a few minutes, because otherwise the rest will be lost. Huh? This question, but just to briefly answer, and this part might be useful for you guys, is measuring this quantity, the average, this is a hard quantity to measure on average. Likewise, these exponents are very difficult to measure with accuracy on average. So I think I've erased it, but where I'm doing the integral, the spatial average, that becomes very important to get any consistent result on the exponent. Now, when you do that, then what you lose is the spatial information, because to get the exponent, which is an average, so you can write down the measure formally, but that's only in a formal sense. But to get the individual sort of distribution of either the exponents or that becomes numerically becomes very difficult. But we can discuss this at the break. That's, Ritik, Siddharth are also, they're the ones who are actually measuring this and not me. So they're the ones who are facing the problem. Okay. So from here, you can, use this because, this is getting a bit tedious for you guys. So maybe, I'll take a break here, give you all a break, and we'll come back and look at a very simple example with sketches to just identify this anomalous dissipation problem, the fact that you can have energy dissipation without viscosity, because all of you studied Newton's laws, right? There's no friction, there's no energy loss. Viscosity, as we discussed in the very first class, is a bit like friction. So if I've removed that, how can there be energy loss, right? So we look at it, I mean, this is exactly what we prove, but we look at it hopefully in a more toyish problem where you can sort of get a better grip on that. I just want to make one final remark. I'm not essentially going to go through this perhaps, is I glossed over many things. Huh? So I glossed over during this proof, I glossed over the fact what happens when L becomes large, capital L, at the scale of the flow. So those are things you might want to read about and worry about. And what I've also glossed over is the fact that now that you have a handle on pi, you can actually use these guys, the inequalities that we just did, just for fun. So remember, we had the structure function, we had the structure function like this, right? And I said that P sigma P will be zeta P. So you can use those sort of arguments to show that the structure function will be nothing but the pth norm, the pth power of the pth norm, however ridiculous that sounds. I mean, that's trivial because there was a 1 over P sitting there, so you cancel that, you're left with the pth power integral. But you can play a similar game, take the pth power of the pth norm and see that you can come up with an estimate of the structure function scaling, which will go as L to the power P sigma P, and some inequalities satisfied on that. So what do we know? I'll just finish here and then we'll take a break and come back. What we know, I mean, you might want to ask us what we know. What we do know is the nature of the fact that zeta P2 you can show this clearly. So for this, I sort of encourage the textbook of Frisch, where there's a very nice section which summarizes what we know theoretically or what can be shown theoretically for these exponents. I pause because I'm trying to, in my head, reconstruct the argument to see if it's greater than or greater than equal to, and that matters in mathematics. So this you need to, and you have certain other proofs related to zeta P plus 2 and zeta P, etc. So those are things you might to worry about. All of them conveniently and happily satisfy the measured exponents that people have. What people don't have is, as you would do in undergrad college, what's the formula for this curve? So that's something we do not have. All right. So let's come back. This is our usual spot. Let's come back. And then let's just look at a simple problem where I will show this, what Jitendra was asking about the pi going to 0, etc., and see if those bounds are satisfied in that problem. And then if we have still some time left, we can have some freewheeling discussions, or I can sort of, I don't want to, okay. The other thing, of course, there are sort of powerful theories to understand this. We didn't go there because it takes us in the world of fractals, etc. And given that we didn't get a chance to talk about attractors, strange attractors in any detail beyond the Lorentz model, I don't want to go there. But if you guys are interested, there are theoretical statistical models which have to do with fractals, which kind of make sense of the nature of these curves. But none of them gives you a formula for this curve, if that's what you're after. Okay, so let's take a break of a few minutes and then we come back. All right, so in the remaining jail time that you'll have, let me sort of do this curve, these two curves, which, so as I was discussing with Anupam, so let me reiterate what I told Anupam. So let me go back and give some broad statements first, just to appear profound. So one is the fact that when you talk about the turbulence problem, maybe Rama had begun with that. So there is no unique problem. That's something that you guys should keep in mind. So there's several problems. They're all important. It depends on your training. It depends on your persuasion, which is the problem that you are familiar with. For example, boundary layers are a tremendously important problems, probably with, at all scales. And it's something that, that probably has a more direct bearing on our everyday life. I mean, this sort of scaling has a direct bearing, but it's it requires a little more effort to appreciate where it has a direct bearing in terms of various things. Okay, so that's one point I want to stress. So for coming from the sort of persuasion that I have, for me, if you were to pin me down, these two, why this is what it is, and this is related to the question of intermittency in turbulence. And this question, which is known as the anomalous dissipation in 3D, these, and that's just a personal bias, these to me appear to be very important problems. And they are related, but in a way that I'll only sort of point out as a by the way right now. They are sort of related to the question of the mathematical question in this field, which has to do with the existence of smooth solutions for all time. We do not have a proof of that. And that question is sharply defined. So y'all are young and y'all are much more creative and brighter than I am. So you guys can go ahead and try to crack that problem. If you crack that problem, you don't have to worry about little things in life, etc. all your things will be fulfilled. All right. So let me now turn my attention, while keeping this picture in mind, to a much simpler problem in some way, and that goes by the name of Burger's equation. So in this room, there's one expert on this who understands this much better than I do. That's Ritik. So you can sort of ask him to fill you in many more details if you want, your TA. And this Burger's equation sort of goes back to the 40s, James Burger's. And what he wrote was this equation. So this is in 1D. And I will work with in the space of periodic functions. I won't go beyond trigonometric polynomials, sin x, cos x, sin x. So this equation has the following form. So you see it has the exact same nonlinearity as the Navier-Stokes equation. All right. Except there's a pressure term here. This is in 1D. The notion of incompressibility doesn't make sense because del x dx u equal to 0 gives a trivial solution. All right. So this is an equation which is in 1D. There is a cousin of this equation, which is even more celebrated for good reason, which goes by the name of the Kardar-Parisi-Zhang equation, where you make a suitable modification on u. You assume it to be some gradient or some height field. We write the equation in that language, and you add a bit of stochastic noise to that problem. And that is a very, very fundamentally, I mean, again, so the expert of that is Anupam, who's sitting at the back. So that the KPZ, certainly much more than I am. So the KPZ equation presumably is one of the most important sort of ideas to emerge in statistical physics, right? I guess Anupam will agree in the last couple of decades, and it has found applications in all sorts of things. I mean, this Burger's equation, I've written it in 1D. I'll do it in 1D because that's all I can do. But this equation has applications in problems of directed polymers and problems in cosmology, problems elsewhere. There's something, if any of you are astrophysics, I don't remember, this is what you may have encountered as the Zeldovich approximation, where you use a certain approximation to understand n-body problems in astrophysics, etc. But let's look at this equation in its simplest form. This is the equation. So there are some trivial remarks I can already make about this equation, which I couldn't do for Navier-Stokes in the higher dimensional problem. The first thing is, I can write this guy. So this is sort of cheating, but I will come back to this issue because Navier-Stokes have been stressing that the viscosity 0, viscosity going to 0, etc. are those limits you can't play fast and loose with. But for example, just to sort of have a mental picture, this essentially means that dtu is 0, where dt is del t plus u del x. Right? That's what's known as a material or convective derivative. By the way, in case you're more familiar with a more conservational form of this equation, you can take this u inside and write it as del x u squared by 2, etc. That helps you to prove some things. All right. So what this essentially means is that the acceleration is 0. What does that mean? That means here I can draw better. So that means this is x. So let's imagine I'm working between 0 and 2 pi periodic functions. So I'm here at 0, 2 pi. And let's say I begin with some initial condition, sin x. Why? Because I can draw sin x easily. That's the only reason. Apparently not. There's an easy solution to this, which is first let me draw sin x and then label. Okay, so this is 2 pi now. You can always rescale things. All right, so the fact that dtu is equal to 0, that means I can imagine this initial condition, each of these points are my fluid points, right? So it's like you take a necklace with beads and you make a sin x curve out of it. Now, the fact that this derivative is 0 means that every fluid element or every bead will have the same velocity at all times because there's no acceleration and there's no viscosity that I've given it initially. So what that means is this guy has 0 velocity, it will stay put. Use a different color. This guy has a little velocity, it will move in time here. This guy will move in time here. This guy will move in time here. Here, I have a problem. I'll ignore that. I mean, it's isometry is the same construction. Here, this guy, when it starts to move, at some point, it will start crossing the particles which are ahead of it. In 1D, that cannot happen. You cannot cross. All right. Here, the traffic rules are more strict than Indian cities, so you cannot cross in 1D. All right. So what that means is at a finite time, and this does not require, I mean, you can show it mathematically more rigorously, but just by this physical intuition, you can convince yourself what that time is. We'll come to that time, but you can convince yourself that at some time, I call it T star, the solution will look like this. All right. The fact that it cannot cross leads to what's known as a shock. So there's a discontinuity in the field. So there's a, the left arm is sort of positive ramp, the right arm is positive ramp with a positive slope. So that's the solution you will get in some finite time, which will work out, but which is something that you can intuitively convince yourself. There are many ways to convince yourself this is not exactly correct because it's bounded by the maximum velocity that it had at t equal to 0. There are many ways you can convince yourself. One way is you can ask yourself, what is the time it has taken for this particle to reach here? I mean, there are many hand-waving intuitive ways. Graphically, you can convince yourself. So another way to think about this, remember I was drawing these lines. So maybe before I go there, let me ask you a question, because if not, then I'll avoid that direction. So how many of you are familiar with ideas of if you change a coordinate system, do you know how you change coordinate system? In the sense, are you familiar with some things which are called Jacobian of transformations? All of you are? Okay, then we can proceed. Okay, so what you can ask yourself is that at t equal to 0, my particles are positioned, let's say A. So this one was at A1, the white one A2, A3, A4, A5, A6. Now, because dtu is 0, they've moved with a constant velocity, right, going forward. So they've changed their position to x. This is what's known as going from an Eulerian to a Lagrangian picture. So Lagrangian picture is my particle coordinate A that I began with. This is a technical thing. So even if you have not come across this transformation, that's perfectly fine. Don't worry about that. All that we are saying is that the position of this particle after some time t, let's say this pink particle here, this particle will be given as x equal to whatever it was at t equal to 0, plus the velocity at that time. That's all it has done, right? It's just moved simply. These are games I cannot play in Navier-Stokes, unfortunately. So this is a map going from x to a coordinates. So I'd like you all to go back because that's not what, because that will take us too far down a different road. But I want you all to go back and find out if this map always holds. You already have a clue. That's because you already saw that as they start crossing, the function becomes multi-valued. So probably, and you need to apply some other rules to get the physically relevant solution to get rid of the multi-valuedness. So in other words, can you come up with an idea when this function will not work? So one way to think about it is the Jacobian of transformation. So you're going from x coordinates to a coordinates. So the Jacobian of transformation will just be del x del a. This is trivially one-dimensional. When that becomes 0, this transformation will cease to exist. And that is the situation that will buy you a derivative on this. And so you can connect the time at which this, let's imagine the shock time. I mean, there's a subtle difference, but that's okay. The time at which the solution breaks down, and that's when you start getting a shock. So trivially, this will be T star, if that's the time, will be equal to -1 over the gradient of U0A. You'll get a lot of T values there because the gradient of sine A will have values which range from -1 to +1. So the physically admissible time will be the smallest time that you will see, and that you will find out what that is. In this example, it's 1. All right. Very good. That's one way to think about this problem. Actually, just to give you a clue, you can actually proceed this by expanding things to higher powers, and you can get a rigorous estimate of what I'm going to say, state as a fact, but you don't have to worry about it. Okay, so this corresponds in a different world, in the same problem, a different way of seeing this shock happening, this multi-valuedness, is to ask the following question. So, okay, when we did Fourier analysis, some of you said you all were not very comfortable. So, you can stop me now because I don't really need it. I have a different way to explain it. But are you all familiar with complex poles, singularities, or that's okay? Yeah, okay. Okay, so my initial condition is sin x. Does it have a pole singularity? If so, where? No. Okay, good. So this function I've written on the real line, right? So as the function at the beginning, there is a pair of pole singularities which is sitting at infinity. So you don't see it. As the solution evolves, so this is on the real line. For this, let's draw an intermediate curve. You see, it's the graph is moving like this, the solution, right? And the shock happens. So for the white curve, there's a pair, I won't draw the negative, the other pair. there's a singularity sitting at infinity on the imaginary line. Those on the x-domain, so it's there. For the blue curve, it has come up close to the real domain. This is the real line. At the shock, this singularity has actually touched the real line. All right. So, yeah, so that's the pole singularity. So this is, so in Burgers, you can actually prove it more rigorously, and you can prove it reasonably correctly just by playing with that map x equal to a plus t u 0a. And Ritik can show you exactly how to do that. But the point is that for the Burgers equation, the answer to the question whether the solution remains nice and well-behaved and smooth for all time, we know the answer. The answer is no. There is a finite time singularity T star when you have either you can look at that picture and say, that's when the shock happened, when the map breaks down, or you can do a complex analysis and you will find that there is, depends on the initial condition, but there is at least one pair of pole singularities for, let's say if it was an initial condition sin x plus sin 3x, there'll be more, where that those singularities touch the real line at some finite time. So you guys can go ahead and try to prove this for the Euler or Navier-Stokes, and then you all are really famous. Okay. So what's the consequence of this? Why did I say that I'll want to work with this? I have these two graphs in mind, but I want to look at a simple problem. So that's the sort of genesis of the simple problem. So one of the advantages of Burgers is that this admits some solutions that we know. And I'll write down the solutions. The solutions will look very similar to what we have there.
So the time we calculated for soft to occur in that, so this time is in that frame.
In which frame?
So we are not transforming time. So this is in the same.
Yeah. So that what you've calculated is exactly correct. So that's T star.
So it is in the same thing, but it dependent on this.
It depends on the initial condition. As you see, this time at which the shock forms is just the inverse of the gradient of the initial condition. So if you choose a different initial condition, and from that formula you can tell me immediately that, for example, if your initial condition was sin 3x, then T star would be 1/3, because the gradient buys you a factor of 3. So it's 3 cos 3x. The maximum of that is cos 3x maximum is plus 1. So 1/3, 0.33. So you can play with your initial conditions to, once you've given me an initial condition, I can tell you when it will happen. That's for nu equal to 0. With nu not equal to 0, but viscosity reasonably small, I should have drawn that, I'm sorry. So at T star, let's say this is the solution of Burgers for nu equal to 0. And for nu not equal to 0, this will really test my artistic skills. At first, I'll get Ritik to draw this for me. You approve? So for any finite viscosity, this is not a real jump discontinuity, but there's a spread, and this spread is of the order of nu, right? Again, these are things that you can show more formally. So what's the solution? So it's a tan. So as I said, we can have interesting solutions to this problem. And the solution, the simple sort of exact solution, if you like, to this equation. This you can sort of do in various ways is say for any general L. Whenever you write such solution, then your mind just check if it's dimensionally fine. And that's what I was doing. L squared on top, nu into t is again another L squared. So at least I'm dimensionally fine, even if I got the factor of 2 wrong or right. Doesn't matter so much. So this solution approximately for large x going to either plus infinity or minus infinity is of the following form. See, it's linear in x. That's where this ramp comes in. This is a straight line. So that's linear in x. And then there's a jump exactly here. And so you switch from, don't take this infinity seriously. It's just to say that when you're away from this shock. And so if maybe I should write it like this is minus L, let's say this is plus L. In this notation, this is 0. And so you have a ramp solution. So if you have a solution, an approximate solution, unlike Navier-Stokes, then presumably I can calculate epsilon, the dissipation rate, exactly, right? And if I can calculate the dissipation rate exactly, then I'm in business, all right? And the reason I'm in business would be the fact that I can take the square of this guy, calculate the dissipation rate, or in the viscosity going to 0 limit where this solution, so this is the 0 viscous solution, this is again exact. So what I will do is I will work out 2 solutions. Solution 1 and I'm going to try and argue that the second solution in the limit when viscosity goes to 0 agrees with the first solution, which is our physical intuition. And if it agrees with the first solution, then you immediately see that this is an example of anomalous dissipation as long as the solution is non-zero. That's because as you take viscosity going to 0, you still have finite dissipation, right? But no viscosity. This dissipation happens because you're losing energy in the shock acts like a black hole to the energy. Okay, so let's work this out. Okay, by the way, this height is just take the difference of these 2 solutions, and this height is just going to be 2L over time at any given point in time. Right. Okay. So the first case is I'm going to calculate what's my total energy. So take the square of this equation, integrate it all everywhere. And then when you integrate this, I won't go through the algebra in the interest of time. You will see that this is 1 over L over T whole squared. That's trivial because time was sticking in there, and that comes from the fact that U of x comma t has a 1 over t globally sitting outside. Okay? Sorry. So this would mean that the dissipation rate, which will just be the rate of change of this energy, if you want with or without the minus sign, this turns out to be, that's the shock width, I'll call it capital delta, let's say, common notation. And this turns out to be okay. So for a system which has no friction, unlike what you remember from Newton's laws of motion, you have a solution which is continuing to dissipate energy without an explicit frictional term. And that's because the shock has formed. So this sort of suggests, but we do not know I mean, people who've worked on this field for long may have an intuition, I don't, is that even in the Navier-Stokes or the Euler problem, is the issue of anomalous dissipation related to the fact that it can have a finite time singularity or not? Because in the Burgers, we know that they're all related. We know the fact that there is a finite time singularity results in a shock. And because there's such a shock, we can show that the viscosity zero solution also has a non-vanishing epsilon. So now to complete the story, we can actually calculate the dissipation rate when you have the viscous solution. So I will write down the final result because I'm running a little late. And the final result would be this is for small viscosity. You have to make the approximation because I've taken the tan hyperbolic, I've squared this, I've simplified for small viscosity. I end with this sec hyperbolic to the power 4 result. And then, as all of you know very well, I take the epsilon nu solution. So the reason I'm writing like this is if any of you have been inspired in this summer, you might be going back and looking at weak solutions for Navier-Stokes, etc., where you write these weak solutions with the label nu sitting on top, which is the standard notation. Now I'm going to take this with the limit nu going to 0. And what should the answer be? Since you all will be able to expand the sec hyperbolic very quickly in your head and take the asymptotics. And if you don't want to do that, the answer is sitting right on top here. And it turns out that the answer will be exactly the same. Right? A similar result for three-dimensional turbulence does not exist. I mean, the statement is as simple as that. And that is, again, probably if you took a straw poll among physicists and mathematicians working in turbulence, what's the big question that they'd like to ask is to find the analog of this result. And this doesn't exist. Okay, so I've taken care of the first curve with the help of Burgers. It's very easy to do. I don't think you all had so much trouble with this if you accept the solution I wrote down, which I didn't derive for you, of course. It's slightly more comforting than what we are doing in the last 1.5 classes, right? With the kernels and everything. All right. Very good. Is there something analogous to this picture that we have? The picture of scaling exponents. Huh? So let's try to do that once. And then maybe we can try to go back to, or maybe not. Then it becomes more common. I just checked the final calculation. I realized that might be a little too much. But let's at least work out that picture. Okay. This is fine with all you guys. If you have an intuitive question or whatever, you can ask me. So of course, I didn't touch upon the conservation laws. I mean, this sort of equations in some limits, they are what are known as integrable equations. You can have all, you can show, in Navier-Stokes, we showed the conservation of energy, something called helicity, something called momentum, etc. Here you can show much more conservation laws within some limits. Huh?
Is there anything special about this particular velocity field? Like, you get this.
Where does this velocity? No, so this velocity field will just come as a solution to the equation that we have.
This is the general solution.
General solution. So you can plug it in the equation and you can see that it satisfies the equation. Right? Very good. So let's just take a look at this curve. What happens? As I told you, this is an intermittent. This is a measure of intermittency. What is intermittency? The fact that I take higher powers. Suppose you had some simple function, and you take the moment phi to the power 2, and you take the phi to the power 4. You can tell me if I got phi 2 going as r to the power alpha, then phi 4 goes as r to the power 2 alpha. That's what Kolmogorov theory is. Huh? So let's look at this simple example and see where this again breaks down. All right. So let's look at the following. Now this is all very easy. You probably don't need me to work it out for you, but I'll do it nevertheless because we are all trapped here. So let us look at the velocity difference across some scale r. So the structure function, you remember, is right. Now, remember I had angular brackets. That means I want to average over all x. So if this distance is r, then I'm going to calculate the velocity difference here, the velocity difference here, 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 here. All right. Now, if when the velocity difference is computed here between these 2 points, or between these 2 points, or between these 2 points, or between these 2 points, this is a straight line. So the velocity difference should just be r. Right? It's a straight line. You know the slope is 1. Difference is gradient times slope. No. Gradient times the separation. Gradient times the slope will be gradient squared, which in case of a straight line is again 1. All right. So that's r. Now there will be occasions when I might be unfortunate enough to take the velocity difference across this 2 points. There's nothing here, so like this. So then what should the velocity difference be? Delta, this amplitude, r doesn't play much of a role. And sometimes I will do it with delta. This I will measure nearly all the time. I'm going to cheat a little, but this I'm going to say I'm going to measure really with some probability which is close to 1. These things are more formal ways of thinking about it, but this is fine. What about this thing? When do I fall into this pothole? With what probability? If my R was huge, am I likely to fall in the pothole more or less? So are there more mores in the room or more lesses? So suppose the separation was like this. I am not following in the pothole. Not yes, 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 yes. But if it was like this, then no, no, no. Only for a small fraction I'm going to fall. So this I will pick up with some probability which should be R over L, the total length. All right. Actually, all these things are scaled with R, but never mind. I mean, you should mind because that comes in when I'm doing which power dominates. So that would suggest that if I take any pth power of this, the probability is not to take raised to the power p, that sticks outside, then the exponent will essentially be r to the power p plus r to the r by L to the power plus into delta. All right. In my calculation, I'm going to measure something which is r to the power zeta p. Right. That's what we did. So if I measure this, when r is small, remember r is going to be less than 1. Everything's rescaled, let's say, with L. So when r is small, then, so it's a small number, for p less than 1, this term dominates. Okay. 0.5 to the power 0.5 and 0.5 to the power 1, which dominates? Actually, I'm trying to take the square root of 0.5 in my head. But right. So for r for p which is less than 1, this chap will dominate. For p which is greater than 1, this chap will dominate. All right. So for the burgers, you get a curve which will be like, it's not Navier-Stokes. So the exponents will be scale as p, not p by 3. And then you have a flat line where it stays constant. So the dimensional argument in case of burgers would have given you something which would just go like p, right? But because there is a shock, why should it go like P? That's because away from the shock, the field is smooth. So everything is Taylor expandable. So any moment, any difference would be gradient into separation. So the Burgers, the naive theory would suggest a curve like this. But the minute you actually look at the real solution, because of the shock, you see a sharp departure. So in that sense, again, it's similar to the turbulence picture. What's actually more interesting, and that we won't do at all, is that if you take the Burgers equation and you force it in certain ways, which are known as stochastic forcing with a certain variance on the forcing, etc., then you get exponents which look suspiciously close to turbulence. They're just suspiciously close, they're not. Where the theory would suggest exactly the Kolmogorov P/3, and the numerics suggests something like this. All right. And so that area is called Burgers turbulence, and the two words are shrunk in a way which I cannot pronounce. So Burgulence or whatever, which is a stochastically forced version of the same equation, which has, and that has to do with the fact that when you force things stochastically, you get actually multiple shocks, which have a certain density, which one can calculate mathematically. That's the interesting thing, how many shocks you have on a given length scale. And so the probability of R over L that I trivially wrote down there changes with that probability. And so you end up getting an R to the power P/3 followed by an R to the power 1. And that's a beautiful system. Again, Ritik has studied that quite a bit, which comes formally from the same set of equations, but has very different physics. Navier-Stokes, as far as we know, including old field theory calculations, etc., the stochastic. Okay, this is perhaps my own view, which might be incorrect, is that the exact prescription of the forcing for this sort of problem doesn't play a huge role. So I wanted to end with a simple example where this, tremendously, hopefully exciting, at least for some of us, sort of results and ideas in fully developed turbulence sort of are easy to show. And so probably the experiments are not wrong, the numerics are not wrong, the theories that we have are not wrong, which sort of gives hope that one day we'll actually be able to explain those two curves, which we haven't. So one final sort of remark, apart from questions that I can sit here for a while with you guys, is that this sort of nonlinear equations, this Navier-Stokes equation, which we sort of built up, it's a coarse graining, which we didn't elaborate on too much. So you can actually begin with a system of particles, and then there are various levels of coarse graining. I mean, for example, Ritik has worked at two different levels of coarse graining, the mesoscale sort of level and the more large-scale coarse graining. How you develop these models which are continuum in nature, so hydrodynamics, if you like, from the simple sort of particle picture, which happens at a much more microscopic level. So that's one area which is beautiful to worry about if you all have time. Instability is something that Rama must have touched upon. She's a expert in instabilities. That's again a fabulous thing. I don't think we've done any vortex dynamics at all in the course. Did Rama do any? She was planning to, but did she get time to do any vortex dynamics? Do you know? Okay, so you all haven't seen how this equation looks when you write it in there. In some of there, since he spoke up, is someone who understands vortex dynamics the best, I think, in this room. So in this building, so you can certainly check with Somav. So that's again an area that is quite fascinating. Then more recently, even for, and this again is a personal bias, even for things which are fluids, but fluids not made, I mean, they're still made out of atoms and molecules. I was about to say something completely incorrect, but fluids which are not of oxygen and sulfur, whatever, SF6, etc., air, but fluids whose constituents can be thought of to be living organisms like bacteria, etc. So take a petri dish full of bacteria. If you've given it enough food and light and love, they move. And so if you sort of look at it from a little distance, you will see a fluid which is moving, but those are the bacteria which are moving. Those are at the discrete level, those are bacteria. I'm not going further in discreteness that the bacteria itself is composed of atoms and molecules. So those are again things which can be at this hydrodynamic description, that is when I take my lens out a little, they can be treated as a continuum description. Siddhartha is a specialist of that, where you can write down the evolution equations for this, and then you sort of try to understand what are the similarities of all these models. So there's a lot of sort of fascinating stuff which goes around in this sort of world of flows, and you can kind of construct it. So you can, I try to give a flavor of something which are slightly more mathematical, that you don't worry about the phenomenology. You are a master of norms and inequalities and Minkowski measures, etc., etc., etc. And then you can again go ahead and prove things, or you can take a slightly softer approach where you're guided by intuition, by experimental results, by results from simulations. That's all that theorists can do, unless you're mathematically very strong with these equations, and then you can make a living out of it.